Morning to one and all. My name is T. Naresh. Here, the subject is electric drives and the static control. And the topic regarding to the subject is the stabilization of the rotor flux oriented control of induction motor with filter by active damping. At first, the abstract is the use of passive LC filters affect the dynamics of rotor flux oriented control induction motor, which drive with the inverter output filter. Therefore, a combined control technique has been proposed in this paper, where the state variables of the filter and the motor have been controlled using the state feedback controller and the proportional integral controllers respectively. The proposed technique has been analyzed and simulation results have been provided for validation. Let's talk about the introduction. Sinusoidal LC filters are generally placed between voltage source, inverter, and squirrel cage induction motor to reduce the distortion in the output voltage of the VSI voltage surges at the motor terminals code losses in the SQIM. Bearing current and the electromagnetic interferences rotor flux oriented control of the SQIM is widely used in the adjustable speed drives. The introduction of the filter network may make the operating point of the RFOC of SQIM drive unstable and may create sustained resonance frequency oscillations in the stator voltage of SQIM. This paper proposes a simple inverter current based active damping technique, which damps out the resonance and the oscillation by emulating the virtual resistance connected in series with the filter inductor in its control structure. It also effectively stabilizes the unstable operating point of the closed loop system without changing the parameters of the controllers used in RFOC. Here, the left side and right side, which is all about the analogy to the DC drive and the analogy to the DC motor. Let's at first talk about analogy to the DC drive. In the DC motor, TE is equals to K phi F IA. Phi F controlled by controlling IF. IF same direction as phi F. IA same direction as phi A. IA and phi F are always perpendicular and decoupled. Hence, TE is equals to K dash of LF into IA. IF into IA. Keeping phi F constant, T controlled by controlling IA, where these are of the space vectors. Whereas analogy to the DC motor is nothing but that of induction motor T is equals to K sine R into psi S, where psi S produced by stator currents and psi R produced by induced rotor currents. Both psi S and psi R rotates at synchronous speeds omega s, where angle between psi S and psi R varies with load and motor speed. Torque and flux are coupled. Principles of field orientation control. Hence, if the angle between phi s and phi r and is is made to be 90 degrees, then induction motor will behave like a DC motor, achieved through orientation alignment of rotating DQ frame on phi r and phi s. Rotor flux orientation control and stator flux orientation control. Here, the rotor flux orientation control and stator flux orientation control is being distinguished and say in a single point of view, that is in the method of diagram making, where T is equals to 3 by 2 into B by 2 into L M by L R into phi R D I S Q minus phi R Q I S T, where T of the stator flux orientation control is 3 by 2 into P by 2 into phi S D I S Q minus phi S Q into I S T. The principles of field orientation control. Summary of the field orientation control on a selected flux vector phi f, that is either phi r, phi s, or phi m. In revolving rotating d phi f difference frame, obtain ISQ phi f from given rotor speed reference phi omega R speed controller ISD phi omega F from psi F from flux reference phi F. Determine the angle of positions, that is reference frame orientation angle, which is used in the d phi f, dq phi f, dsqs in conversion from vs dq phi f output of the current controller. In the stationary frame, obtain the reference data voltages VABCS fed to the PWM inverter feeding the induction motor from VSDQS using the DSQS ABC transformations. Rotor flux orientation control is all about how the d-axis of PQ rotating frame is aligned with phi r, where hence phi r d dash is equals to magnitude of phi r, where phi rq is equals to 0. Here the torque producing current and field producing current were distinguished ISQ and IST respectively. Similarly to IA and IF in DC motor, decoupled torque and flux control. And at last, we are talking about the anti-damping method upon the rotor angle decrease, where the G2 replaced with DFIG wind farm and only synchronous generation, where G3 replaced with a DFIG wind farm synchronous generation. Conclusion is stabilization of rotor flux oriented control of induction motor with filter by active damping also effectively stabilizes the unstable operating point of closed loop system without changing the parameters of the controllers used in RFOC. The idea of proposed AD technique has been illustrated with mathematical expressions and justified through stability analysis. The instability of the operating point and the impact of the AD technique are experimentally demonstrated on RFOC of VSI fed SQIM with filters at different test conditions. And at last, the reference are from Controller of Induction Motors Academic Press, Electric Motor Drives, Modeling, Analysis and Control, Power Electronics and AC Drives, Hard Vector Control of the Induction Motor course, North University of the Nottingham. That's what how the topic regarding to the stabilization of the rotor flux oriented and the control of the induction motor with filter by active damping is being completed. Thank you.